All right. Well, let's go ahead and kick it off. Welcome to the fifth installment of the CNCF's webinar series. My name is Ariel Jatib. I'm an ambassador here at the CNCF. I also organize the New York City Kubernetes meetup, and I'm a co-founder at a company called StackPoint Cloud, where we provide turnkey Kubernetes solutions. A couple of house rules: you're all on mute. But there is a chat window and a Q&A section where I encourage you to add questions, and then I'll try to find opportune moments to interrupt the group and present them. We're also recording the session, and we'll be sending that out to everyone after the event, along with a link to the presentation deck. So without further ado, I'll hand it over to Mark, who will be taking it from here.
Hey, thanks very much, Ariel, and welcome everyone to the webinar. Storage has changed a lot in recent years as the data persistence requirements of cloud-native apps have outgrown the traditional enterprise storage. This webinar provides an overview of the evolving cloud-native storage requirements and data architecture. What we'll discuss here is by no means exclusive. Everyone's requirements vary, and we're fortunate to have a rich, expanding ecosystem of cloud-native storage technologies. Before we begin, I wanted to introduce today's speakers. I'm Mark Balch, VP of Products and Marketing at Diamanti, joined by Eric Hahn, VP of Product Management at Portworx, and Clint Kitson, Technical Director of Code by Dell EMC. Thanks very much for the presenters and everyone who's contributed to delivering this webinar. Cloud-native storage is a fundamental part of the CNCF reference architecture, since most applications require some form of persistent data. We often hear about stateless microservices, and it's true that stateless workloads like web and app servers are foundational to modern cloud-native apps. But microservices, however, usually have some dependence on persistent data stores. Whether they're retrieving your photo album or confirming your restaurant reservation, that data has a life cycle that's far beyond the momentary API call or transaction that's executed by the stateless application tier. In this presentation, we'll talk about modern applications, their diverse data persistence needs, and the new approaches to satisfy those requirements. There is no one solution. Data persistence used to mean choosing between a limited set of NFS and SQL database options. Now the cloud-native ecosystem takes an extensible open source approach. You've got abstractions and plugins that gives users choice to select the storage technologies that best fits their needs. So Eric, over to you.
Thanks, Mark. Hi, everyone. This is Eric. Pleasure to be here. I wanted to start our story with a real-world example, so let's just jump in. And if we start with the premise that everything is possible, it's not enough to say that cloud-native means it works, and not being cloud-native storage means that it doesn't work. Instead, let's focus on some important questions. The first of which is avoiding a monolithic architecture. So instead of a monolith, how can we have layered services that cleanly separate when we need to and be seamlessly bound when it comes to the user experience? So how do we have these user experience and achieve it in terms of development and immediacy for the user? And so from the left to right, what I want to describe here is a prototypical or an example application. And from the user experience on the left-hand side, I have users who might be using their mobile device, they're accessing images, they're uploading pictures. They can post in the middle, they can post and rate things and drive locations and maps. And on the right-hand side, there's a bunch of trends and stats, leaderboards that make it part of the interaction. So all of these, if this is an example of an application, how can I think about enabling this within my own in-house or cloud environment and have this cloud-native feel? So next slide, please. So if I talk about it and look at the cloud-native patterns with storage, and if I go from the left to right, what I might see here is that we have, Mark, could you go back one slide, please? Go forward two. Okay, so let's go back one more. It looks like one slide might be missing, but so from a cloud-native pattern with storage, what I might describe here is that I have thousands of events, and if there's a before, the before might be something like a batch processing, where I have tons of events coming in and they're launching into a front end, and as those front ends are processing their data, they're being batch processed through a thin POSIX layer, and that batch process then goes to a MySQL. And so what ends up happening is you start to aggregate and serialize the demand. So instead of having that experience, if I look at a cloud native pattern, what might a cloud native pattern look like? And from a cloud native perspective, what I instead expect is to process the demand on demand in a current real world fashion. So from what I can think about there is that instead of having a front end that goes to a batch and that batch goes to a MySQL, I could let developers there pick the stacks of choice. So instead of just having two kinds of application stacks, they might have Kafka. And so they could take a message system like Kafka that takes heavy load, and then they start to process incoming requests in real time using something like Spark. So these can become evolved into something like a SMAC stack. But then they start to create these leaderboards and trends, and they can use Cassandra to cache the top user and stats, and they can still use the MySQL to bring it all back. So instead of having a serial experience where I'm going into a front-end layer to a batch processing to a MySQL, I can instead have this cloud-native pattern, and this cloud-native pattern means that I have real-time response, a lot more user interactivity, and that's all enabled by the fact that I'm using things like containers to let developers pick the stacks of choice and have the packaging that allows me to have this flexibility. But it's important also to have this kind of density. Otherwise, all this becomes not really possible in production. So if we go to the next slide. And we talk about the first iteration of container storage and what it might look like. And what we see here is that if I'm thinking about all the stacks that people want, we can talk about containers and the value chain it provides the higher level services like Docker for building, publishing containers and allowing versioning reuse. But instead of the higher level services, let's focus at the container resources, the lower level of how we control and compartmentalize CPU memory and storage. And so instead of focusing at the apps, let's focus on what happens in production, and that containers create this ring fence. And because this is a resource level that enable apps to pick, or developers to pick and choose the stacks of choice and get density in production, this ring fence is subdividing the host's resources. And the first iteration of the ring fence might have looked something like this. It's a useful bootstrap, but as I look at that bootstrap, it's thinking about things of how do I create a handshake, and how does a container on the left and a container on the right get storage? And what I might do, or what people have done in the first iteration of container storage, is do a host mount. And what all that really means is they do this handshake, they get a bootstrap, and they handshake and they get the local storage. And this proto-container native approach, it doesn't really give persistence. So it kind of works. Your applications can get storage. Each container can take a portion of the hosts, but at the same time, there is no persistence beyond the host's existence. So if the host reboots or dies, I lose access to my data. And since containers can float anywhere, it's important that I have a pattern that makes the lifecycle independent. And it becomes prohibitive for stateful workloads because they need the ability to manage performance and capacity. And if I have this approach where I've tightly coupled the container and the host and the storage, I don't have this flexibility that's important for me in production. Next slide, please. So this one we spoke to, we'll keep going. So the aha here is to give containers persistent volumes. And that's to say that beyond the handshake, how do I get access to storage? But the PVs themselves, they're important because the persistent volumes become the building blocks for running cloud natives. And persistent volumes have to be their own first-class citizen. And they have to live independently of the host and the container, because only then can we have the right building blocks for being container native. And it's important for us to be able to run and keep the applications and their storage to be portable across the environments. And in some ways, that's what container native is enabling us. So an easy way to illustrate this, next slide, please, is to describe it this way. The aha, or the translation of container native, could look like this. It's persistent volumes in the bottom half, this volume 1 and volume 2. And these persistent volumes, they could be coming from a mesh of hosts and external systems, or however your provider implements, but they're external. And these volumes have a different lifespan than the host and the container. And we'll come back to a Kubernetes example that flushes this out with a diagram. But before I do that, I'd like to turn it over to our next speaker, Clint Kitson. Clint?
All right, thank you, Eric. Glad to be here. Hello, everybody. So let's take a more pragmatic view of how this actually works today. Within the diagram that Eric showed, we showed a driver or a storage plugin, which is really the glue between a container orchestrator and the backend storage platform. It's important to note that these are all control plane operations only, and the job of this plugin is to really orchestrate the resources to bring a volume to the host that needs it, and that enables the container orchestrator to take over and actually make that available to the proper container. Today, we've got 3 major platforms in the cloud native space that enable this type of extensibility, these types of plugins. First, you've got Docker, you've got Mesos, and you've got Kubernetes. Now, there's 2 main ways to describe how this functionality and this interoperability works. The first is the in-tree method, in-tree storage plugins, and this is a method that Kubernetes solely subscribes to. This is a great approach in terms of user experience because there's no additional installs or things that a user needs to know how to run. But it's difficult for the Kubernetes code base because that means all of the storage plugins are encapsulated inside of the code base. So it's great for user experience, but difficult in the long term. There's also what we call out-of-tree storage plugins. And this is a common method that all 3, Docker, Mesos, and Kubernetes subscribe to, an approach that's actually being furthered through another initiative that we can discuss a little bit later. But these out-of-tree storage plugins, there's really 2 flavors of them. First is the Docker volume driver interface, and this is commonly provided by way of Docker and Mesos. They use the same interface for extensibility. And then there's a Flex interface for Kubernetes. So these interfaces provide the glue or the capability for any of the external storage platforms to assist in these control plane operations that get the data volumes where they need to be for the containers. Next slide. So the goal of this is to do exactly what Eric described, right? We want to have this plugin that interoperates and brings the volumes to where they need to be. We want to enable the lifetime, or we want to enable the data to survive separately from the container, the pod, the host, any of that container infrastructure. We also want the application itself to be able to define what its requirements are for storage, or we want the engineers or developers or operators to be able to define with the application what type of storage the application needs in order to satisfy the workload. And then the last thing is that we know that the pattern we're describing here is portable, and in terms of cloud native, right, that's a really important facet to the cloud native ecosystem. We want to make sure that we're portable across clouds. We want to make sure we're portable across container orchestrators. In general, like this pattern where we do interoperability is much better and much more portable than if we try to abstract any of the capabilities. Next slide.
Thanks a lot, Clint. So cloud native storage takes many forms. There's really many different data types. It's not just files and SQL queries like you might have had years ago. There's unstructured data and metadata, streaming data, logs, blobs, right? And so every application, every developer is going to select the data types that are most advantageous for the application. And no single storage technology is going to meet all these needs all the time while also being cost effective and effectively scaling in terms of performance. So that's why there's this broad ecosystem of storage solutions available using the plugins, the open interfaces that Clint just talked about. Each API is optimized for specific types of data. But underlying all of these different data types, abstractions, are block storage services. And according to cloud native principles, they should be interoperable so that you have the choice and flexibility to go where you want and get the right level of capability and cost. Persistent data, which is really what we're talking about here, has to be protected somehow. It can be handled at the application layer, at the middleware layer. It can also be handled at the storage services layer. Sometimes it's handled at multiple layers, depending on what the application requires in terms of redundancy and time to recover from failures. Then you've got other services like data reduction, compression, deduplication, encryption. All of these can exist at multiple layers in the stack. It's important to have interoperability because between all of these different layers so that you have choice about where you're going to go. When it comes to storing these data types, there's also the issues of consistency. Some applications require very strong consistency. For example, if you're handling someone's credit card information, you typically want to make sure that a glitch is not going to cause a, losing track of who ordered what and what people paid for. But some other applications, like storing photos, it may be okay to have eventual consistency, where as long as the photos arrive a few seconds later, maybe a couple minutes later, that's going to be okay for your application. So as with anything, there are trade-offs between cost, throughput, and service levels. And so having the interoperable cloud-native storage APIs and abstractions lets you mix and match what's going to be the right thing, right? Another example of that is being able to choose different types of media. Flash and hard drives or spinning media, of course, have very different cost and performance characteristics, and different types of data and different types of applications may favor one or both. So how do you choose the cloud-native storage approaches that are right for your application? And I said approaches, plural, because most likely you're going to choose multiple technologies, even for a single application, because many applications have different types of data within the same application. So one of the first things is to recognize the difference between frequently accessed hot data and less frequently accessed cooler data. If you can tolerate eventual consistency for some data sets, you'll typically save a lot of cost and complexity. However, your application then has to deal with that. So your application has to deal with temporary inconsistencies across locations. It works for some, but not all, right? If you expect to be able to cut over immediately without losing anything, you have to then handle that at the application level if you've chosen a storage technology that doesn't have strict consistency. I talked about financial applications before, photos before, right? Each of these is a trade-off between what's implemented at the storage services layer and what's implemented at the application layer. Some developers choose to implement caching on their own so that they can decouple from the underlying storage infrastructure. But some applications, it's very difficult to reinvent the wheel and try to build your own caching, so you rely on the storage system to do that. But the point is that cloud-native storage should automate and abstract that underlying storage infrastructure, so the application isn't necessarily tied to one single vendor or technology, and you can choose where you want to implement those capabilities. So just like Clint was saying earlier, a key enabler for this is integrating with the container runtime and the orchestration software. Rather than manually configuring storage, the infrastructure should be managed automatically as a consequence of deploying your containerized application. And as with other cloud resources, cloud-native storage is going to be pooled and it's going to be shared across multiple tenants for the maximum efficiency. And so you need to make sure that you have isolation and you have quotas so that one group is not stepping on another group. So all of that has to be managed intelligently, enforced at the appropriate service level. So it's no longer a model of one size fits all, where you just buy one monolithic storage solution and you just pay the same cost and scale penalties for a given level of performance across. You're going to make choices that are specific to your application needs. Over to you, Clint.
All right, so now we start to think about, in my environment where I'm running, whether it's in a on-premise cloud or in a public cloud, do I have cloud-native storage? Do I have some storage that can satisfy what Mark was describing there? And one of the first things that you can look for is, am I interoperable with these COs and the runtimes? There's a pretty easy way to take a look at this. You can go to the Kubernetes storage plugins and you can see whether there's any in-tree plugins that support your storage platform. You can look at the Docker plugin store to see whether there's Docker plugins that help you interoperate. So interoperability is a pretty easy thing to take a look at, and it's really important to understand that if you're running in a cloud right now, such as a public cloud, the storage services that are there, they may actually satisfy the requirements you have for your application. But if they don't, then comes time to start thinking about what a storage platform may look like to help satisfy that. So if you're going to be looking at these platforms, there's some characteristics that you want to keep in mind. You want to make sure that the core capabilities of these platforms are advertising, such as the size of the volumes, the type of the volume, whether it's spinning disk or the capabilities of IOPS that are available for the volume. You want to make sure those types of core capabilities are there so that you can make them available to empower your applications. From a data services perspective, your applications may benefit from snapshots, replication, encryption, any of these key data services that we're familiar with the storage world. Those should be available through interoperability. A platform that advertises role-based access control is going to be important. So if your platform is able to differentiate access levels, then you're going to have more use of that platform. So as you give the keys of the kingdom to developers, you give the keys of the kingdom to your container orchestrator, you're able to limit at a granular level how much of that storage platform is available, whether it's the volumes or whether it's the size. All these capabilities should be included in this RBAC. A really important one is the elasticity of the capacity and the performance. So as you consume from this cloud storage resource, whether that's on-prem or off-prem, you want to make sure that from a consumer perspective, that you're not limited, right? That the consumer kind of feels that there's this limitless capability of consuming data one way or another, and that you're able to properly meter that so you can make sure that people are doing the right thing. So elasticity of these cloud services is very important. And then the last point here is the life cycle and the operations being automated. If you've got a storage platform that you're using where it takes a lot of manual intervention, then that's likely going to impact the elasticity that the consumer feels of that resource. So you want to make sure as much of this is driven through software as possible to create this cloud storage service. There's some key things to stay away from. So if you're looking for this interoperability and you want to get your data to your applications, you probably don't want a complex storage platform. When we can talk about this in the form of being hardware defined. So a great example would be Fiber Channel. Fiber Channel is kind of a middleman between a storage platform and a container host, and that represents another resource that needs to be automated in order to make that connection happen. So in the case of hardware defined resources, that may be more difficult to interoperate with. The other thing to look for is slow control plane orchestration. If you have application owners who are looking to launch their applications, maybe it's a short running task, maybe it's a long running task, but if it's going to take a minute to get a volume orchestrated and made available to an application, that may cause some operational problems. So we're looking for orchestration to attach a volume to an application, which may happen in a matter of milliseconds, and it may be a few seconds. I think those are all probably acceptable for the broad majority of use cases. And so if you're thinking about, hey, do I need something different in the data center? Mark defined a lot of these application requirements that may exist. And so you want to take a look at that to say, hey, I may have something that's interoperable and work, but maybe there's application requirements such as snapshotting or replication. Maybe there's things that my platform doesn't have, which is going to cause me to think about another storage platform to support my workload. And then the other one here is, in my data center, maybe I'm thinking about it, running containers in a greenfield environment. So if it's greenfield, then you probably don't have a shared storage service yet on-prem that you can supply storage for your containers. So you're going to want to think about a platform that can check all these boxes so that you can build a shared storage service that you can interoperate with your container hosts. If all of this, if you're not checking a lot of these boxes with the storage platforms that you have, another alternative, which is going to be very common on-prem, is to think about whether you have a virtualization environment to support a lot of your back-end services. So if you have Fiber Channel or you have hardware-defined things in the data center that's being extracted by virtualization, then it's probably that virtualization layer that can help you in terms of interoperability, and that can make it much simpler, and it can make it a much better experience for your containers. So next slide.
Okay, let me, if I can chime in a second with a couple questions. This is Ariel. So at what point does, we have a question from Mark, at what point does a traditional storage such as pushing volumes from a SAN into VM stop scaling and you need to adopt a container-centric approach?
Yeah, good.
Yeah, I think the question about scaling is an interesting one, because I think the comparison would be very similar as you look at that compared to virtualization environments. At what point do my VM stop scaling with my storage platform? I think you're going to find that at some point. I think the question is really am I acting efficiently? am I acting efficiently for all the workloads that I'm trying to introduce? And so if I'm thinking about running applications, maybe it's Cassandra. Cassandra has its own distributed data layer. If I'm thinking about running that on top of virtualization, is that the most matter of
and to shift slightly the focus, the cost. Like how does cost compare from like monolithic volumes to cloud native, highly available approach?
Anybody else want to feel that? Mark, do you want to take that?
Yeah, I mean, so every solution is obviously going to have different pricing, relative performance, and to scale. You know, I'll answer that by kind of continuing from the previous question. Is that, let's say that your application needs to be able to store blobs, whether it's, you know, videos people are uploading, photos, you know, cash receipts, whatever it is. You can have an option, for example, to push that over an HTTP interface to an object store without having to deal with, you know, back-end file systems. And you have a very simple HTTP interface, and you may not need to access those blobs very often. So one question to think about in terms of if you're trying to trade off cost and capability, you know, do I need that fiber channel environment Clint was just talking about, or can I use an object store, which is going to have many fewer requirements and dependencies on my application stack, and it's more portable? I can move it to a public cloud, a private cloud, pretty much anywhere I have HTTP access, I can access that object store, right? So what is really different, I think, about cloud native storage is that it's not a one-size-fits-all. It's saying that, look, my application has a variety of data persistence needs. I've got infrequently accessed blobs that I can put on an object store. I've got, you know, financial transactions I'm going to put into my SQL database on my block store. I've got, you know, key values that I'm going to be looking up when I'm trying to validate users with Cassandra, right? So there are more choices, there are more tools. Not everything is a hammer. You have lots of different tools to effectively and efficiently build your application.
I'd like to also jump in. I think I agree with everything Mark and Clint said, and just to tie back to Clint's point, and Mark, your most recent area, your most recent thing, and then more provisioning. Do I slow down my time to production? And so there are things like a physical limitation, like how many HBAs you might have. Some systems are 8, but that's a very vendor-specific point. But I think it's important to think about both the runtime experience and what Mark Balch was saying, as well as the monolithic aspects. And so the bill of materials in a public cloud could look like the fact that I have containers going against EBS, but what happens as EBS gets stuck and starts moving? And we'll talk a little bit about that hopefully throughout. So just wanted to add a few things.
Okay. We have a couple more questions I'd like to chime in. We have Dennis who says, like his biggest concern is that all these container management platforms provide a storage in unique ways. He also highlights the challenges with SAN being speed and how fast SAN admins provide storage, which I think you guys touched on slightly, along with the idea, you know, something that really interests me from the presentation is the idea that I have portability across orchestrators. And so I guess can you highlight a little bit about, Dennis, if I'm misrepresenting your question about what feels like some portability, please feel free to chime in.
Yeah. And just to be, I think, more clear, like I think the point is great. Dennis said SAN, and when you say SAN, you tend to be discussing a team of people that manage a SAN within all these different companies. And you know what we're moving towards is a highly automated environments where applications can just automatically satisfy their needs and concerns from a storage platform. Mark was talking about the differentiation of data services and how we're getting more efficient with providing those in different ways to help satisfy the apps. And that's definitely not a SAN discussion. But getting to SAN, like if your concern is, hey, I've got a SAN team, they may not move as quick as my developers need to move, then what you think about is okay, the SAN that we're describing, is there interoperability in place, right? Are there plugins that make it easy to at least get volumes provisioned and made available to my container host? If the answer is yes, then you can definitely look at the plugins that are out there to make use of the SAN. If the answer is no, and the SAN team takes too long to provision the volumes, et cetera, they don't give you the right access, I think what you start to think about is in your data center, it's very likely that you have a hypervisor or virtualization involved. So you've got something that's abstracting that SAN. So in that case, you would have the SAN advertising, volumes to your hypervisors. And then that's a matter of the interoperability question really has to do with your hypervisors to the container orchestrator. So the COs are making use of the hypervisor, which has abstracted the storage. It makes it much easier for you to consume that environment.
Yeah, one comment also there, I agree with that. And, back to Dennis's point around the orchestration software, I think about interoperability at kind of two different planes. There's the data format and API, whether it's block storage, whether it's a SQL query, an HTTP push or put for an object store. There's that, which is, and there are lots of interoperable options there, right? If you understand block transactions with Linux, you can do that on many different platforms. It's a very open system, for example. Same with HTTP requests. But then I think, Dennis, you're also talking about interoperability at the orchestration level, right? And that's, back to Clint's slide earlier around the plugin architectures. And there's a lot of work going on in the CNCF and the community overall to drive commonality around the control plane interfaces, so that if I'm using Kubernetes or I'm using Mesos or any other solution, I have a consistent operational experience in terms of how do I specify the types of volumes and persistent resources I need, and then no matter what orchestration I'm using, I can get that the same way. Now, to be honest, we're not quite there yet today. There are variations, as you've seen, but the community is working towards that. And I think everyone I've seen has that interest to try to make that more uniform, so that there are fewer speed bumps to defining your persistence requirements and then deploying them along with the application.
And Mark, I think that's actually a great segue to pass it back to Eric at this point, because he can show example for us of what a consistent experience may be, no matter what your plugin is under the covers.
Yeah, thank you for that. And Dennis, I like the question as well. So let me just talk about it from what we were describing earlier as the aha moment of giving a persistent volume and what it could look like in Kubernetes, but also how it provides that cloud portability and the aspects that are also changing. And so if I think about an application and it has Kafka, I could bundle those containers in pods, and those pods will need to get volume. So that lower right-hand, the persistent volume is the end result that gets returned, but how do I get there? And what becomes important is, as we're all discussing here about SANs and other forms of storage, this storage class becomes a way to have this abstraction. So I can have my best of breed storage class for this set of departments or this set of use cases, and I can have different storage classes for this provider and that provider, and that's represented in the lower right in the green. So what ends up happening, and why this is important that we have the right approach, is that it yields what Dennis and everyone else is asking about this portability, is that the pod says, I want a class of storage, and I'll give into a very specific example. And it goes into a persistent volume claim. That claim goes and seeks a volume, and it goes and finds the storage class. And that storage class, I'm using a dashed line to describe the fact that it's happening behind the covers in the drivers, is that storage class will then return to me a volume that gets mounted. And so now that pod has a persistent volume. But if you click one more click mark, the important thing here is that this upper layer becomes the portability aspect. So I can take this pod definition with the PVC or the persistent volume claim. The persistent volume claim will talk about I need 8 gigabytes of storage. It'll talk about the environments or the important attributes for the pod. But at the same time, this upper box or this tan enclosure is portable across environments, or that's the intent here. And so if the storage class happens to be implemented for EBS in the lower left with Amazon, or it happens to be Google Cloud Storage or your vendor of choice, hardware or other, it becomes possible that I can have the same application portability. And in some ways, that kind of flexibility is what gives us the ability to run in production with developers picking stacks of choices or Redis, Kafka, running that and describing what they need in the PVC, but at the same time, infrastructure ops teams have some flexibility in terms of how they satisfy it. And then your data and someone else's data is separated, so I don't have this notion of this proto approach with cloud native, this proto approach of being host bind mounts. Instead, everyone has its own clean volume, and that volume lives independently of the pod. So I have both the lifecycle satisfied as well as this operator versus developer separation, so I can have truly flexibility with my ops and my development. And before I go into the next, if there's any questions about this, happy to chime in or happy to respond. So why don't we go to the next slide? And so this is just going to fill out and describe in more detail, and this is a little bit of a pseudo syntax, but in describe in more detail the same sequence that we just mentioned in the past. And so this is a nice way to tie up everything we've been talking about. So this is our last slide, and it gives a concrete example. And so here I have a pod, and it's talking about the Kafka. That Kafka has that volume, and that volume itself is using the PVC. So it's actually the PVC that becomes important. So that PVC itself was in the upper half. And Mark, if you click next. And so the first step here is that PVC is created, and that PVC says, I'm looking for a volume. That volume needs to be 8 gigabytes, and I'd like it to be of the fast type, or that fast implementation. And I can start to decorate it with things like labels. But at this point, a 10 gigabyte volume could satisfy this PVC, a 9 gigabyte, but this pod is asking for at least 8. So from that approach, the application definition can be run in dev, test, and production. And if I go to the storage class itself, the storage class itself will then say, I implement this fast, and I have all this provider-specific provisioning that can then make it the best for my ops team. But at the same time, the application is completely portable on the pod and the PVC level. And if you click one more time, and this is the last, is that the persistent volume itself is the one that actually gets satisfied. So the persistent volume becomes where I write to the application actually writes to a persistent volume, and that persistent volume in this case is EVS, or it could be GCEPD, or it could be something else. Now, to get higher levels of portability, or to have another form of portability at the data level, that's a separate topic. But at least from the application definition and from the description that I want to bring into different environments, I've solved the control aspect. Now, the data gravity is the next level, and that's a little bit beyond the scope of this discussion. But in some ways, I wanted to highlight how all that operator versus developer has been separated out in a clean fashion in one form. And as everyone's pointing out, this is getting better and refined as we go along. Why don't I pause there? And that's basically my last slide. And I wanted to say thank you to everyone and make sure that we made time for questions.
Cool. Thank you. All right. So a couple questions coming in. Let me ask one from Jason, and then I have another one from Irat. How does OpenEBS contribute to the cloud-native storage ecosystem, particularly with regard to its use as an underlying block layer for higher-level persistence?
I would think of something like, and I'm not a technical expert on OpenEBS, but I think based on the question, there's a little bit of a description of it in there. But it sounds like another storage platform that can provide a layer of persistence on top of any type of storage resources. I think that you're going to find a lot of platforms emerge out there. You're going to find more and more of them being software-based. And in the future, you're probably going to find them being, managed as cloud-native applications. So I can't really point to a single project right now to say that's contributing to the future foundation of storage in a cloud-native landscape. I think that where we are is that interoperability and making use of the cloud services that are available is likely the most common approach. But there's definitely a lot of enabling features and capabilities and differentiation among platforms that are emerging to make it more interesting in the future.
Great. Let me go next to next one from Ira. They ask, how does this work in sequence with rolling upgrades in case of deployment and PDs and PDCs in the case of stateful sets? Tried to massage that a little, but I think
yeah, I think I'll take a stab and others can jump in. I mean, the stateful set itself stateful set is just like another type of, you could think of it as a pod with a controller. And I didn't separate out stateful sets, but if I went back to my diagram, you can use stateful sets and start to reuse a lot of the same concepts. And so the idea of the rolling upgrade could be the fact that I set the replica count and start to change it based on the number that I actually want to create. And so that control is possible, but now in terms of the actual data you're writing, it has to be a separate control aspect. And maybe this is why the open EBS question was there, is because the stateful set is about the control and how I create volumes and start to grab capacity at the same time. That control is not necessarily talking about how that data is consistent from what has been written to disk. So that's possible why the open EBS question was there, is like, how do I make sure the data is there? And that's up to a provider like an open EBS. So then I would say the unification of these two topics is, how do I take a stateful set, put in some layer that controls the data, and then start to make this rolling upgrade. And that would be possible, but it's also back to the topic of what your app is. With Cassandra, it'll start to work with eventual consistency. With a Postgres, it can work if you have the ability to synchronize the data at the data layer.
Can I add in here?
Yeah,
point two. I think in an interesting area that the cloud native storage space is going to be tracking is the operator automation that we're finding. And how I simplify that is to say that whether it's Hadoop, Cassandra, any of these like distributed data layers, which are more complex to operate, there tends to be kind of two books that you read about them. One book is how what I give to a data scientist, which is how I consume from something like Hadoop, and then the other book is how I operate the thing. And so when you say rolling upgrade, I tend to be thinking about it in terms of the container storage platform and not necessarily the application itself, but they're interrelated topics. Because as I do rolling upgrade on the container storage platform, I need to take down some of the nodes at certain times. And in order to make the right decision, I probably need some application logic so that I know what I can take down at a certain time and what I can't. So there's this form of operator automation which is emerging, which enables us to encapsulate like the complexities of some of these applications. And that's going to be important that we start to integrate this operator automation into the awareness that we're providing and the interoperability of the storage layer. So I think that rolling upgrade question, like from a basic perspective, it's going to work fine today for your simple apps if we're talking about rolling upgrades of like the container orchestrator. But from a more complex perspective, as I have many nodes and instances that satisfy like what this application is, there's more operator automation that's taking part that we're starting to see emerge, which is where I think the conversation and the area starts to get really interesting.
Yeah, one final point there, just think back to earlier in the presentation, Eric covered a couple of slides, the difference between host-centric storage and container-centric storage. And when you're talking about rolling upgrades, you want to decouple from the physical platform so that a particular node can go away either during an upgrade or during a failure. And you're going to always bind that persistent volume to the container no matter where it lives. So if you have to move the container, if your replication controller ends up restarting that container somewhere else because the original instance had to be killed for the rolling upgrade, you need to make sure that storage is accessed regardless of where the container gets spun up again. If the storage system is having a rolling upgrade across scale-out nodes, that storage system has to deliver availability of those APIs, both the control APIs and the data APIs consistently. And obviously, back to the previous point, you have to make sure that the app can tolerate that and can resync the data that was transacted during that brief period of time where that cutover occurred.
Great. And I think answered another question we had from MS, and I think the last one we have here sounds like it's Kubernetes specific. It says, how fast can we expect a decision, a conclusion on the container storage interface? And I'll defer slightly to Mark or Sean, but I believe the CNI, which is related to that, is up for review starting later today. But unless anybody has different information on that.
Yeah, I think this is all pretty public information. The CNI is up for vote at the CNCF as as a project, an incubated project. So that's the container networking interface. Early in the presentation, we showed a slide that we've referred to a few times, which showed some of the complexity of interoperability today in terms of storage plugins being in tree, out of tree. CSI represents kind of an industry agreement between the container orchestrators on what their needs are. And also between initiative. And that is very much active right now. There's a working group, which is available through CNCF, the CNCF Storage Working Group, which you go to the GitHub page .com/CNCF to see. So you can sign yourself up if you're interested in participating in the discussion. We're currently at a 0.10 versioning of CSI. So there is a kind of an active spec out there that Google through Kubernetes and Mesosphere through Mesos and Docker and Cloud Foundry have all actively participated in. So things are making progress. There's a spec that's out there, and I would look towards the next, I think, 6 months, so towards the end of the year, to start to see some production implementations of CSI within the container orchestrators and plugins that support that functionality.
Awesome. Yep. And there's a link, Sean, through, I'll share a link out with the group in chat. But with that, we'll bring it to a conclusion, this 5th installment. Thank you so much, Clint, Mark, and Eric, for attending. And register for that now. And big thanks to the CNCF for making all this happen. Have a great afternoon.
Thank you, everybody.
Thanks, everyone.
Thanks, everyone.